And here it is. This is a real life situation. I do not recall how long ago it was. I'm going to guess maybe about 12 or so years ago. And I don't even remember where we were getting ready to go. But we were going on a trip. It may have been a weekend camping trip. May have been longer than a weekend. I think it might have been longer than a weekend. I don't remember now. But we're all ready to go. It's the day, the departure day. And lo and behold, I discovered something very distressing. We had a small leak in the water heater. The water heater was dribbling water out of this bottom panel where the electrode goes for one of the two heating elements and the thermostat and everything. It was dribbling out of this to the outside and onto the floor. Oh my, we can't leave the house like that. So what in the world am I going to do? We're getting ready to go on a trip. I don't want to cancel the trip. What do we do? So I got a pan. Oops, wrong tool. I got a pan and put the pan under here. And then I rigged up a little funnel that I attached to the side of this thing. Taped it on here. So, oops, grabbing the wrong thing here again. I created my little funnel thingy here that kind of went like this and forced the water into the pan. Okay, pretty good. Then I realized, there's only so much water that pan can hold before I'm in trouble. So then I got to thinking, well, I can't have a taller pan, because if the pan is, say, this tall, by the time the water's not going to go into it, it's not going to work. I have to keep a pan lower than the leak. So what am I to do? Well, I grabbed hold of another pan. Oh, I keep using the wrong tool here. I grabbed hold of another pan. I put another pan right there. I mean, this is for real. I'm not making this up. In fact, this is what inspired the demo that I showed you earlier. This real life scenario. I took 3 pans. I think it was only 3. It's a long time ago. And I filled up these tubes with water. Of course, that's not going to work if you don't prime it. So I had to put, now the tubes were actually way down here, like just about touching the bottom. I didn't make my tubes in the diagram long enough. The tubes were touching the bottom, kind of like that. There. Then I had to put a little bit of water in here. Oh, again, wrong tool. I had to put a little bit of water in the pan so that it came up to the level of the tubes here, and a little bit of water in this pan, and a little bit of water in this pan. Now I knew that as this pan filled up, just like in the demo you saw earlier, the water level here is going to rise, but now we have higher pressure on this side, lower pressure on this side, so the water in the high pressure side is going to go right up this tube to the other side and start to fill up this pan. But as that pan fills up, we're now going to have greater pressure on this side and lower on that side. So this water is going to go right up the tube down here and start filling up this pan. So now I'm filling up all 3 pans equally as the leak progresses. Another cool thing I discovered later on, again, I don't remember the exact circumstances, but I know that I had this apparatus set up after we returned from our trip. And the water's getting kind of deep. I thought, I better bail some of this out. So I get a container. And I very stupidly started bailing out of all 3 pans. Then I realized, whoa, that's way too much trouble. All I have to do is bail it out of any one of these pans, and the other 2 will go down to meet it. So as long as I didn't allow the water to go below the tube, as soon as the water goes below the tube, then this water will go, and I've lost my siphon, we call it. So that system worked very nicely for me. When the guy came to deliver the new water heater, he was quite impressed with my setup. He'd never seen anything quite like it. Well, that's what happens when you're dealing with a physics teacher. You end up with clever solutions to very difficult problems. It got us through our trip and back again, and continued working until we were able to get the guy to come in and replace the water heater. So, physics in real life. Now, we move on to the remainder of chapter 13. I'm picking up at page 257, and Pascal's principle. I feel like we've mentioned Pascal's principle before, but maybe not. Pascal's principle says, if I increase the pressure on a liquid, that increased pressure is going to be transmitted equally throughout the liquid in all directions. So, what's the big deal? Why do we care? Again, let me say it once again so you don't have to rewind it to hear that again. Pascal's principle says that when I add pressure to a liquid, that pressure, that increased pressure, will be transmitted equally in all directions in that liquid. So here's the cool application of that. If I have a very strangely shaped container of, say, water, like this. All right, I fill this thing with water, and then on top of the water here, I put a piston. A piston being a little thingy bobber. Oops, that's horrible shape. Let me try that again. I put my piston here. That's better. This piston is designed to be able to slide up and down inside the tube, but it has a rubber gasket around it so the water cannot leak past it. This, by the way, is what you find in brake systems in cars. When you push the brake pedal in your car, you're actually pushing a piston into a cylinder full of brake fluid. The brake fluid does not leak past the piston, but the piston is able to push the fluid down into the cylinder. On this side, we're going to have another piston, but this piston is huge. Uh-oh, my computer is about to die. I forgot to plug it in. Stand by one moment while I go plug in my computer power. Sorry about that. And problem solved. Okay. Glad I noticed that. If my back had been turned, the thing might die while I was in the middle of finishing this chapter. Ooh, 5%. Ah. All right. Now, here's the cool thing. Suppose the area under this piston is maybe 1 square inch. Okay? So we have 1 square inch of area. Area under this piston, 1 square inch. Now, remember the definition of pressure, the formula for pressure. Pressure equals force divided by area. All right, suppose I now apply, 5 little old pounds of force. Yeah, I like the old English system. I'm not a fan of metric. I'm just old-fashioned. But suppose I push down on this piston with 5 pounds of force. So what's the pressure going to be then? 5 pounds of force applied to 1 square inch, force divided by area, 5 pound force over 1 square inch of area, we're talking 5 pounds per square inch. So I'm applying 5 pounds per square inch. 5 pounds per square inch. I guess I could, how about if instead of writing square inch, how about if I write inches squared? Be easier to read that way. Inches squared. Okay, 5 pounds per square inch. Now, that pressure of 5 pounds per square inch that I'm adding to the, of course, there was already pressure in the liquid, of course. Pressure determined by depth. More pressure down here, less pressure up there. Right now, that's irrelevant because now we're talking about the added pressure I'm putting on it. Pascal's principle says that added pressure will be transmitted equally throughout the liquid. So I'm getting an additional 5 pounds per square inch there, an additional 5 pounds per square inch there, an additional 5 pounds per square inch there, and everywhere. Throughout the liquid in all directions. 5 pounds per square inch on all the surfaces, everywhere, including here, and here, and here. What's that? I've lost my big eraser. And here, and here, and here, and here. 5 pounds per square inch. Think about what that means for a moment. That means 5 pounds of force on every square inch. This piston is huge. Let's assume for a moment that this piston has an area under here of about 100 square inches. Just making up numbers. 100 square inches of area under this piston. But we're applying now 5 pounds of force to every square inch. 5 pounds per square inch. 5 pounds per square inch. Here, 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 everywhere. If I'm applying 5 pounds on every square inch, and I've got 100 of those square inches, then how much force am I getting upward on this piston? Yeah, 5 pounds on every square inch, 100 square inches, we're talking 500 pounds of force upward on this piston. If I were to change the numbers here, suppose I made this 20 pounds I push with. 20 pounds times 100 square inches would be 2,000 pounds. I could just about lift my car with that. In fact, that's basically how the lifts in garages work. Something similar to this concept. So, but you say, well, wait a minute, this can't be. How can you multiply force like that? What about things like conservation of energy? This shouldn't be possible, that you can push with just 5 pounds of force here and get out 500 pounds of force over there. How is that possible? Think back to an old chapter. This is an example of a simple machine. What are we doing? We're trading force for distance. Consider if I push this down, say that far from here, suppose I push it down to here. Consider the amount of fluid that I'm pushing out of that tube. If I take that little bit of fluid and spread it out over this whole thing, it may only rise about that far. In other words, yes, I'm getting more force, but it's over a much smaller distance. If I'm getting 100 times as much force, the piston will only rise 1/100th as much. You say, well, what good is that? Well, it makes it possible for me to lift 500 pounds with a 5-pound force. Yes, I have to push farther to get this to come up just a little bit, but hey, it depends on what I'm trying to do. That may very well be exactly what I need. How else can I lift 500 pounds with a 5-pound force? It works. It works. By the way, the brake system in your car, very similar. When you push the brake pedal, you've got this thing behind the dashboard of your car called the master cylinder, and there's a piston in here. This thing is filled with brake fluid. Inside the car, you're pushing a pedal that pushes the piston in, and it pushes brake fluid out a tube, actually out a couple of tubes. And one of these tubes, if I'm not mistaken, I haven't done a whole lot of work with brake systems, but if this is your car, you've got a wheel here, a wheel there, a wheel there, and a wheel there. We're looking down on the car, okay? One of these tubes will go to a device, let me put that somewhere else. We'll go to a device here, but it will also branch off and go to this one here, and the other tube will go over here, and it'll branch off to this one also. So when you squeeze this fluid out of here, it's going to be squeezed into a similar contraption on all 4 of these wheels, which will push on a piston on these 4 wheels, and that piston in the wheels is going to force these things called brake pads together, squeezing a disc that rotates between them with the wheel, and it squeezes and makes the wheel stop. And that's basically how brakes work on a car. I don't think Paul Hewitt has any diagrams of brake systems on cars, although it's a wonderful application of how pressure in a liquid, Pascal's principle, works in cars. I understand that when the first person who came up with this idea for brake systems in cars, folks thought it was crazy, that you're going to stop the car by pushing fluid through a little thin tube like this. You've got to be out of your mind. They wanted to have a big steel bar that went from here to the brakes. But someone came up with the idea of using fluid instead. And a lot of folks were like, what? But it works. Which also means, by the way, if you get a leak, then that's going to be a problem. Brake fluid is going to come out here instead of going here. That's why, by the way, they have 2 separate sides to this. And I'm not going to try to illustrate it, but this is actually split into 2 separate parts here, so that if one side fails because you get a leak, oh no, the other side still works, and you get some braking power on this wheel and on this wheel, and you're not necessarily going to die. Now, if both sides get a leak, that's when you are in trouble, because both sides of the system will fail. By the way, if you do get a leak in one side, something kind of cool happens. There's a sensor in here that senses the difference in pressure, from one side of the system to the other. If this starts leaking, you're going to have low pressure on this side, higher pressure on this side. There's a dealy-bobber inside the brake cylinder here that senses that difference and sends a signal to your dashboard, and that little brake symbol comes on. That little brake symbol on your car can come on because you have a leak in the system, causing an imbalance in pressure, or it can come on because you have not enough brake fluid. There's a reservoir up here where brake fluid is stored, and the brake fluid goes down into here, and if you have a small leak, say over a number of months, and the level of the fluid gets too low here, then that light will come on. In fact, that happened with my Miata just the other day. My brake light came on. I couldn't figure out what was wrong. There were no leaks. Brakes were working fine. What in the world's going on? And finally, after about a week of worrying about it, it hit me. I need to check the level in my brake fluid reservoir. And it was still in there, but it was just low enough to trigger the red light on the dash to come on. So I got some brake fluid, poured it in, everything's fine. Light goes out. Of course, that light also goes on when you put the parking brake on. So that light has multiple functions. Low fluid level, a leak in the system, parking brake is on. There are other possibilities as well that could cause that light to come on. But that red light on your dash means you've got a problem. If it doesn't go off when you take the brake off, you need to check out what's going on. Don't just ignore it, because you might find yourself coming up to a red light and not be able to stop. All right, more practical applications. I really do want to finish this chapter, so, there is a diagram on page 259 of the basic idea of how it works in a service station. A little bit different than what I'm showing you here. They use, instead of a piston, they use compressed air. All right, now, next concept. Surface tension. Surface tension in water. There are two things going on with surface tension. We've got this thing called adhesion, and we've got a thing called cohesion. I hope I spelled this correctly. Adhesion and cohesion. Adhesion is a word we use to describe when one thing is attracted to and stuck to a different kind of material. Example. If I have a container here, and I've got a drop of water clinging to the inside, that water is attracted to the glass. The water will hang on to the glass. It'll stick there. I'm sure someplace in this room, because I've been playing with water today, I'm sure there's some examples of that. Yes, I have water that is stuck right here to the side of this flask. It's being held onto the side of the flask by adhesion, water to glass. But we also have something called cohesion. Cohesion is where water is attracted to water. So if you've got a drop of water, say, just hanging in space, it's kind of hard to do here, but on the space station you could do it. You've got a drop of water just floating around in the space station, no gravity. It's going to tend to form a round spherical, is that redundant? It's going to form a sphere, a round blob. Why? Because all these particles of water in here, all these particles, let's call them molecules, all these molecules, let's expand that view. There's a big drop of water. We've got molecules of water in here. Each one of these molecules, by cohesion, is attracted to all of the molecules around it. Well, if that molecule of water is attracted equally in all directions to the molecules around it, what's the net force? Zero. It's not going anywhere. But consider the molecules on the surface of the water, like right there. That molecule is attracted to all his friends inside the particle, but he's not attracted to any water molecules outside because there aren't any out there. So in that case, what's the direction of the net force? Yes, inward toward the center of the drop. That makes that drop want to stay in that position. It wants to stay in that way. It doesn't want to go flowing out that way, and it doesn't even want to move out sideways. It just wants to stay where it is as it's being pulled inward. And all of these molecules around the surface here are all being pulled inward, and the result of that inward pull of all these surface molecules is what we call surface tension. It makes the surface of the water act like there's a skin on it. There is no skin. Please do not ever make the mistake of thinking there's some kind of mysterious skin on top of the water. There is no skin on the water, but it acts like there is. Have you ever been to a pond or a slow-flowing creek where you have those little water bugs? Check those guys out sometime, up close. You've got the water here, and I need to erase that, start that over. Let's take a bug first. We've got a bug. This is a bug, and he's got his little buggy feet sticking out here like this. He's got a whole bunch of little buggy feet. He's got 6 buggy feet, so we'll give him 6 buggy feet out here like this. He is able to walk on the water. The water, if you look up close, try this sometime. Look up, that bug, by the way, is probably more dense than water. He should sink. But he's able to walk on the water because of surface tension. If you look closely at these bugs on the water, you will see this. It's not something that, oh, you can't really see that. No, you really can see this. You'll see the water kind of go under his feet like this. You'll see the water actually bending under his feet, because that water is acting like it has a skin on top of it. And his feet don't break through, because all these water molecules want to cling together, and they don't want to let his feet come through. Now, of course, a larger creature, a squirrel, is going to easily break through that surface tension. He doesn't even realize there is surface tension, because he's just going to, when he falls through, he's like, I thought the surface, this is a squirrel talking, I thought the surface tension was going to hold me up. Oh, well, I'm just a dumb squirrel. And he falls in and drowns if he can't swim. But the bug is so lightweight that the surface tension actually can hold him up. Now, here's something you have probably, probably seen before. Oh, excuse me. Let me turn on the lights here for a moment. And I'm going to detach the camera from my tripod here. Oh, can we see your tripod? Yeah, this is what my studio looks like. Not much to it. Saw Mr. Leach out there just a moment ago. I don't know where he is now. But, now, here is some water. The water I used in my demo a little while ago. And, wow, can I do this with one hand? I don't know. It's tricky. I'm trying to get the paper clip on the fork. You may have seen this before. This is one of those kind of experiments that kids do at home. But you don't very often try to do it one-handed. This is not working well. Okay, I want to try. Oh, come on. Yeah, you're enjoying watching me struggle here. Okay. Come back. Ah. And somebody out there saying, Mr. Why don't you try this, that, or the other? Well, I can't hear you, so I'm on my own here. Okay, there we go. I've got the paper clip on the fork. Now, behold. Hopefully this will work first time, because I do not want to have to do that again. And notice, we would all agree, I think, that a paper clip is definitely made of steel and definitely more dense than water, and it should sink. But it's not sinking. Why? Because the surface tension is holding it up, just like with the water bugs. And you can clearly see, it hadn't occurred to me how nice this was going to be, you can clearly see how the water bends around it underneath. I don't know if we can see this from the side. That'd be cool if we could. Not so well. Oh, look at that. You know something? It looks to me like the paper clip is actually suspended slightly below. Look at that. The paper clip is actually suspended below the water level. That's awesome. I've never done this before. Come on, focus. Can you focus, please? If I touch that, does that make it focus? I don't know what that did. It changed the brightness, but it doesn't want to focus. But maybe you saw it for just a moment. Rewind it, you'll see it. So another cool thing is If that paper clip is magnetized, and I tried earlier to magnetize it slightly by using these magnets to rub on the paper clip and magnetize it. If it's magnetized, that paper clip will now act like a compass. If I turn it to go the other way, if I did manage to magnetize it, it will turn itself around back the other way. Oh yes, it's working. We have ourselves a compass. It's pointing north and south. If I turn it a little bit, it will turn itself right around the other way again. It's not acting like a compass, it is a compass. Now if it touches the sides, that might ruin everything. Pretty neat, huh? Now it's not pointing exactly, oh there it goes, it's turning around, there it is, it's back where it was now. Very nice. Now I'd like to try one more thing, but I didn't think about this in advance. I don't have any soap in the room, and I'm not going to go try to find any. But soap has an interesting property to it. Soap does what soap does because soap reduces surface tension. If I were to take just a small drop of liquid soap and just drop it on the water, that paper clip would instantly sink to the bottom and there would be nothing I could do to get it to float again because soap reduces surface tension. Why do we care about soap reducing surface tension? Well, let me concentrate on putting you back where you belong first, and then I will tell you why we care about soap and surface tension. I have had the experience where back in the old days, a long time ago, in a galaxy far away, I used to actually use a blackboard, and my favorite chalk was this particular brand of rather hard yellow chalk. And that was all we knew about back then. Yeah, there were a couple smart boards, not smart boards, a couple of white boards around with markers. Those were kind of nice. But mostly I used chalkboards and chalk. By the end of the day, I would be covered with yellow chalk. My hands were covered, my sleeves had chalk on them, my tie had chalk on it, my face had chalk on it. I would take a white cloth at the end of the day and wipe my face, and it would come up yellow. I'm sure like miners have black lung, I probably had yellow lung. It couldn't have been healthy, but I was always breathing and living in chalk dust. Terrible. One of our teachers, who also used chalk all the time, was actually allergic to chalk dust. How he survived, I do not know. But what I would discover at the end of the day, I would go to the restroom and I would just put my hands in the water, rinse off my hands. I'd see all this yellow liquid coming off my hands, and I'd wash and wash and wash until no more yellow came off, and turn off the water, dry my hands, and my hands would still be yellow. Then I would go back, try again, but this time add some soap. Add a little bit of liquid soap, and all of a sudden the soap turns yellow. I rinse them off, more yellow fluid goes into the sink, and now my hands are clean. What's the difference? The soap reduces surface tension. Surface tension not only does this, surface tension also prevents the water from wanting to go into the crevices in your skin, into the pores or in between the fingerprint lines. The water doesn't want to get into the small tight spaces where that chalk is hiding. Reduce the surface tension with water, reduce the surface tension with soap, and now the water is able to get down into the deeper crevices and wash out the chalk. Pretty cool. That's also why you put detergent in a washing machine. Water will be able to get deeper into the fabric and wash out the gunk if you add soap to it, which reduces its surface tension. Try this sometime. Find a pond. No, don't do this. That would be awful, but it would be interesting. Find a pond. Take a little container of liquid soap. Pour it into the water and watch all the bugs go, ah! Like this. Can I do this? I don't know. Ah! Oh, he brought the water. I thought I could do it without the water. Never mind. Not worth the trouble. Or is it? No. I thought I could make the bug drown, but never mind. No, don't do that. That would be pollution. I don't think we want to have soap in the water, and it would be very cruel to the bugs. So don't do it. All right. Let's see. What else we need to say about? Oh yes, some very important other concepts here. By the way, you know the concept that drops of water look like drops of water are shaped like this? No, they are not shaped like that. When water droplets fall through the air, they actually form, my eraser has gotten small. I don't know how to fix it. Your water droplets will actually be spherical. Now they will undulate as they travel through the air doing weird things because of air friction, but they'll basically be spheres. They will not be that traditional teardrop shape. No, that is a myth. Something else about, this is more new concept, I'm sorry. This is not, we're moving on from surface tension now to something else called capillarity. Capillarity, a very neat concept. If I have a container of water, well, I need to erase that little line, because with water being attracted to glass, but also being attracted to itself, something interesting happens. The surface of the water here, when it gets close to the glass, it's going to be attracted to the glass. It's going to be pulled up the side of the glass like that. Because the adhesive force of the water to the glass is greater than the cohesive force. So the water's going to be pulled up. How far up will it be pulled? It'll be pulled up until the point where the weight of the water being held up above the surface is equal to the force of adhesion to the glass. If it tries to go up too far, then the water weighs too much and the adhesive force is not strong enough to hold it up. But it'll go up until the force of adhesion equals the weight of the water being suspended. So when it gets to the ends here, it'll go up like that. Kind of neat. You can see this, just an ordinary glass of water. I can see it right here in this beaker, but it'd be a little bit difficult to show it to you. But let's take that to the next level here, another step. What if I put into the water a thin tube? Let's open that tube up. Okay. If I put the water, the thin tube into the water. Now what happens is, the water going up the tube is attracted to the glass of the tube. And the same thing that happens here happens inside the tube. The water will rise up the tube. The thinner the tube, can I do a real thin tube? That doesn't look much different. The thinner the tube, the higher it will rise. Because there's less water weight and still the same amount of surface area, so the adhesion to the glass can pull it up even farther. That's how trees get water to the top leaves of the tree. Capillary action. The water is being pulled up actually by adhesive forces to the sides of the little tubes inside the tree trunk. The water is pulled up by the adhesive force. What else needs to be mentioned? And of course, a wider tube, it'll rise up not as far. Oh, and I should make this diagram a little more accurate because the water in the pan here is also going to go up like this. This water will go up like that. This will go up like that. And you've got this thing, this adhesive thing going on all over the place. So that's called capillary action, where the water is pulled up the tube because of its adhesive force between the water and the glass. Now let's see. Oh yes. What if, on the other hand, what if we have a pan of mercury? Now mercury being 13 times more dense than water, mercury also has super powerful cohesive forces. Mercury is attracted powerfully to itself. When I was a kid, I may have mentioned this before in class, when I was a kid, we didn't know that mercury was dangerous. No one did. Go figure. And as a kid, we used to actually play with mercury. Mercury is so... You guys are missing out. Don't do it because it is poisonous, but back in the old days, mercury was so cool. You have two little balls of mercury, very high cohesive force. If you put mercury on a surface, it doesn't do like a drop of water. No. Nothing like that. You put mercury on, say, a glass surface or any surface, and it's going to do this instead. It's going to sit there in a neat little ball. And you can touch it and it'll roll all over the place like a little ball. If you have another drop of mercury here, when these two touch each other, because mercury has such a strong cohesive force, when the two touch each other, they go like bing, and instantly merge into one big drop. It's really neat stuff to play with. So what happens, since mercury has such a strong cohesive force to it, and a relatively weak adhesive force to glass, what happens if you have a pan of mercury? Well, it's not going to do this, but rather mercury, and I've actually witnessed this, mercury will do this in a container. I used to have a little bottle of mercury, and you could look at that mercury in the bottle and see it doing precisely this. Now, if I break the surface and put a tube in here, well, because mercury is more strongly attracted to itself than it is to the glass, it will actually do this, just the opposite of what water would do, and it will not go up the tube. It's clinging to itself so tightly it will not break loose and go up the tube, so it's going to sit down here like that. That's what fluid would do if you put a tube into, that's what mercury would do if you put a tube into a bucket of mercury. Mercury is pretty neat. It doesn't wet things because it has so much cohesive force, very little adhesive force. You can try to soak it up in a paper towel, ain't happening. In fact, in the bottle of mercury I had, there were some impurities in there. There was like a little piece of cloth or something in there, and it just kind of sits on the top, a little piece of paper towel maybe, sitting there on the top. It won't go anywhere, it doesn't get wet, it doesn't go down, it just sits there. You could float on top of a giant vat of mercury. You're not going to be able to sink down in that mercury because, yes, just like with water, if you're floating in mercury, first of all, it has a very strong cohesive force, therefore very, very, very strong surface tension. So you could be like the bug walking around on the surface. But in addition to that, you don't have to go in very deep at all for the weight of the displaced mercury to equal your weight. So yeah, you could float on the top of mercury. In fact, you'd have a hard time getting down into the mercury because there's so much pressure down here. So anyway, enough about mercury. I think that comes very close. Whoa. Forget